Hello everyone and welcome to our review of the physics seminar worksheet on Newton's laws of motion. We're going to walk through the questions and answers together, clarifying the key concepts. Please have your worksheet in front of you. Let's begin on page 1 with the warm-up questions. Question 1 asked, why is it harder to start pushing a heavy piece of furniture than it is to keep it moving? As the answer on your sheet says, it's because static friction is greater than kinetic friction. Think of it this way, when the furniture is at rest, the microscopic imperfections on its surface and the floor have settled and interlocked. To get it moving, you need to apply enough force to break those bonds. That's overcoming static friction. Once it's sliding, the surfaces are bouncing and skimming over each other, creating less resistance. This is kinetic friction, so the peak force needed to start the motion is always higher than the force needed to maintain it. Question 2. When you jump, you push on the earth and the earth pushes back on you. Why don't you see the earth accelerate? This is a great question about Newton's third and second laws. The forces are indeed equal and opposite, but as the answer notes, the Earth's mass is enormous. Newton's second law tells us that acceleration is force divided by mass. You have a small mass, so that force gives you a noticeable acceleration. The Earth, however, has a mass of about 6 trillion kilograms. When you divide that same force by the Earth's immense mass, the resulting acceleration is so infinitesimally small that it's completely impossible to measure or perceive. So yes, the Earth does accelerate, but by a negligible amount. Question 3 was about the difference between mass and weight. The answer is spot on. Mass is the amount of stuff an object is made of, its intrinsic inertia. It's measured in kilograms and is constant everywhere. Weight, however, is the force of gravity acting on your mass. Since weight depends on the local gravitational field, it changes. Your mass is the same on the Earth and on the Moon, but because the Moon's gravity is about 1/6 of Earth's, you would weigh much less there. Question 4 asked, can an object be moving if there is no net force on it? Absolutely yes. The answer correctly refers to Newton's first law, the law of inertia. An object in motion will stay in motion with a constant velocity unless acted upon by a net external force. Constant velocity means moving in a straight line at a constant speed. If the net force is 0, the acceleration is 0, which doesn't mean the object is at rest. It just means its velocity isn't changing. And question 5, the last one on page 1, what is the reaction force to our weight? This is a classic. Your weight is the gravitational force the Earth exerts on you. According to Newton's third law, the reaction force must be equal, opposite, and act on the other object. Therefore, as stated in the answer, the reaction force is the gravitational force that you exert on the Earth. All right, that covers the conceptual review on the first page. Now let's turn to page 2 for the main problem, pushing a 100-kilogram crate up a frictionless ramp. You can see the setup in the diagram provided. Task 1 asks for a free body diagram. We have 3 forces. The weight mg acting straight down, the normal force N acting perpendicular to the ramp's surface, and the applied horizontal force F. Task 2 asks what constant speed implies. As the answer states, this is the key. Constant speed means 0 acceleration, so the net force must be 0. The forces are balanced in all directions. For task 3, we resolve the horizontal force F into components parallel and perpendicular to the incline. As written on your sheet, the component parallel to the incline is F cos theta, and the component perpendicular to the incline is F sin theta. Task 4 is to apply Newton's second law along the incline. Because the speed is constant, the upward pushing component must balance the downward pulling component of gravity. This gives us the crucial equation shown, F cos theta equals mg sin theta. Task 5, at the bottom of page 2, asks us to solve for the magnitude of F. The calculation for this is shown at the top of page 3. So turning to page 3, we see the calculation for F. We rearrange the equation from the previous page to F equals mg sin theta over cos theta, which is mg tan theta. Plugging in the values, 100 kilograms, 9.81 for G and 30 degrees for the angle, we get the final answer of approximately 566 newtons. Next, in task 6, we determine the normal force. Looking at the forces perpendicular to the ramp, the normal force N pushes outwards, balancing the forces pushing into the ramp. Those are the perpendicular component of gravity, mg cos theta, and the perpendicular component of our horizontal push, F sin theta. The equation is N equals mg cos theta plus F sin theta. Using our value for F, the calculation on the sheet shows the normal force is about 1133 newtons. Task 7 asks what would happen if the ramp were no longer frictionless. As the answer correctly states, friction opposes motion. Since we're pushing up the ramp, friction would act down the ramp. This means the force F would have to increase to overcome both gravity and friction. This leads us perfectly into the optional extension at the bottom of page 3, where we add friction. Question 01 asks us to recalculate the pushing force F with a coefficient of kinetic friction of 0.10. The force balance equation along the incline now has an extra term for friction. The steps are laid out for you on the page, showing the numerator and denominator of the final expression for F. After solving, we find the new required force is about 705 newtons. As predicted, this is larger than before. And finally, question 02 asks for the new normal force. We use the same formula, N equals mg cos theta plus F sin theta, but we plug in our new larger value for F. As the calculation shows, this gives a new normal force of about 1202 newtons. This makes sense. Pushing harder horizontally presses the crate more firmly into the ramp, which increases the normal force. This concludes our review of the worksheet. The key takeaways are the power of free body diagrams, the strategy of resolving forces into components, and a clear understanding of how Newton's laws apply in different scenarios. Well done.